Welcome back to the tutor. And we're still on electrical engineering 3. And on today's video, we focus on a star route. The concept is really simple and straightforward. So, as I said, the most important part of all this calculation is to master your phase sequence. Calculation is simple, just Ohm's law and the calculation of power. So we're gonna have a look on exercise 2.1, and we're gonna discuss only the star load, just to have a look, to have an idea on how to deal with a load that is a star connected. So in the problem, we were given our negative phase sequence, and our reference is EA, and then now you're gonna draw your phase sequence as I draw it. If you don't still not understanding it, you can go back, because now we are just focusing on problem solving, because the phase sequence we have explained it and I put a I mark on it to say that you need to master it. So already something you need to write down is that the problem when it was given, there was a mistake. The impedance that you're looking for is ZA, okay? And then this given one ZC, and that's given one ZB. So there was a mistake under the question when they were busy typing, okay? So how do we do this? Because now they ask us for the unknown impedance, which is ZA. But remember, in order for our loads to operate, it needs a phase voltage, because you can see that it's always a voltage between C and N, or A and N, or B and the neutral points, because we have a neutral point, so it's going to be a phase voltage. So when you do calculation for IB, you basically apply your Ohm's law, but this angle here for EB, you are going to get it from your phase sequence. You do the same, your Ohm's law for C, but this angle here, you are going to get it as well from the phase sequence, okay? But remember, they give us the neutral points. We have a neutral point. So the neutral point is the current that is going away of the junction. The three currents are going in the junction, applying Kirchhoff current law, Kirchhoff junction law. The sum of the current into a junction equal to the sum of the current out of the junction, which is the neutral current. So automatically we're gonna have a current A that is going to be the unknown, so that we can get our current A. Once we know what is our current A, we apply again Ohm's law to get our ZA, and therefore we gonna get the value of our ZA. And you can see it's basically simple and straightforward. Okay? But remember, why are we dividing by square root of 3? Okay? Because the given voltage is a line voltage. Can you see? Because you can see that it's a line voltage. So you divide it by square root of 3 to get the phase voltage. Simple. Can you see? And then to calculate the power across that impedance, you apply just the complex power formula, you conjugate the current, but to make sure that this voltage is a phase voltage, which means you need to divide it by root 3, and it straightforward. Okay? But we're gonna have a look on as well on one of the another example, which we can say it question 2. Question 2 here, what they add here is just about, they give us some configuration so that we can look for our total impedance. Because remember, with a total impedance, when you have a resistor and an inductor connected in series, what you need to do is to get that impedance. And sometimes you may be given as well the two connected in parallel, but the concept is still the same. You just need to know that this is an impedance and I need to get the total impedance of my circuit, and it's really simple and straightforward. So in this case, as you can see, what we were given here, it's just that they give us a resistor in parallel with a capacitor, and then we get given in phase B the resistor in parallel with an inductor. We're given a resistor in parallel with a capacitor. So we need to get, first of all, to get what's going to be our ZA. So our ZA is going to be a parallel between a capacitor and a resistor. So as you can see, first of all, I change my capacitor to a capacitance, so that when I apply the parallel circuit, I can get the value of my ZA. I do the same for the branch of ZB. I calculate my inductor to, I change it to inductance, so that I can apply my parallel of the two. But remember, in electrical 2, when we are discussing, we say a pure resistor, a pure capacitor, a pure inductor. With a pure capacitor, as you can see, it's always at the angle of what? -90. Pure resistor always at the angle of 0. Pure inductor at the angle of 90. Pure capacitor at the pure resistor at the angle of 0. So you need to remember those small concepts from electrical 2. So when it comes to the branch C as well, we have a capacitor which we change to capacitance in ohm value, because it's only the capacitor. It's going to be always at the angle of -90, and therefore you do the parallel of the two. So after getting what's going to be your ZA, what is your ZB, what is your A, now you can start with calculation. Calculation are just simple and straightforward. I know my ZA, I know my ZB, and I know my ZC. So in this case, it's just that they give us in form of a component. You need to get the total impedance first in each phase. Okay, and another thing that you observe is that they give us a cos here, which was our reference voltage, and then we know that with the cos we always have to add 90 plus 90 degrees, because our supply is always a sine wave, and therefore we divide it by square root of 2, because it's a instantaneous value. We change it to RMS, therefore we're gonna have this to be our EBC. Our phase frequency is a positive phase frequency, and the reference is this. You know already how to draw, and therefore when you come to do a calculation, it's just Ohm's law. You are looking for IA, IB, IC. You check this voltage, the given one. You can see that the given one is a line voltage, therefore we divide it by square root of 3. Okay, but what is the angle of EA? EA is 180. How do we know it? We go into the phase sequence, and then we come, you can see the voltage EA is 180. That's the angle of the voltage EA. When you come to EB, for IB as well, you take the given voltage, which is a line voltage, you change it to a phase, because you need a phase voltage, and then you go to a phasor the diagram, your phase sequence, you take the angle of EB, and then you substitute it there. You do the same for C, you do the same for everything. You can see that the calculations are really simple and straightforward. Okay, and then we were asked to calculate the total power in the circuit, then calculate this one for SA. It's just a complex power formula. Remember, why do we divide it by square root of 3? Because the given one, it's a line, but here in our calculation we did a phase. Simple and straightforward. Okay, so when you look here, you can do the calculation for your SB, the total power across that impedance. You do the same for SC. It's really simple and straightforward. But once you have made a mistake into your phase sequence, and you don't check if the given voltage is it a line or a phase. If it's a line, you change it to a phase, because it's a star load. Okay, and then again we're gonna go and calculate the total complex power, which is basically the addition of the 3 power, and then therefore we have our complex power. We know already that if the complex power is given by this, if you change it to a rectangular form, this will be your active power and that will be your reactive power. You know this simple concept as well, and therefore our power factor of the circuit, we're going to consider the angle of the total complex power. Simple and straightforward. Okay, and again we're going to have a look on our question 6, which is the last question under the load circuit, and again they give us a combination of a resistor and a capacitor. Okay, so which means we need to get their total impedance. We change the capacitor to capacitance, so that we can get our ZA in branch A. it's going to be given by this because it's a combination of a resistor and and with capacitor. You look for your XL inductance so that you can get your ZB. ZB is a combination of a resistor and an inductor. We have your ZB. You change your capacitor to capacitance, and then now you can calculate your ZC, which is the addition of XC and those coil and resistor. Okay, before you draw your phase sequence, you check what is the reference voltage. When you look here, you can start to give us the voltage BA, but we always have the three line voltage. What are they? It's AB, BC and CA. This will always be our three line voltage. So if they give us something that doesn't appear on these three, we need to change it to this form. So we were given the voltage EBA, so we need to change it to AB, so that you can say here we have AB. But to do that, we need to add or subtract 180 to this angle here, so that you can have that voltage. And then automatically we're gonna get our EAB at the angle of 0, so that you come here, negative phase sequence, the reference is EAB, okay, which is a line voltage. You draw your phase sequence as we explained. Then you come to apply your Ohm's law. Okay, but when you're applying your Ohm's law, you can see that the given voltage is a line voltage, but in your calculation you need the phase, so you're gonna divide by square root of 3 to make it a phase voltage. And therefore we were asked to calculate the active power in the load. You do a calculation of the active power for each impedance. For PA you do for PB, you for BC, and then the addition of the 3 will give you the total power. And then you can see that this is just a continuation. You are just playing around with your Ohm's law, you are playing around with your complex power calculation, you are playing around with line and phase. So you need to identify when is it a line, when it's a phase, and how do I change a line to a phase to a line. So those are the small things that may happen, but everything is really simple and straightforward. Any question, challenge, please always ask it in private or in the group. I will assist you.